All right. So I just wanted to give you an idea of different places where we can store energy within a system. Okay. So places to store energy within a system. Okay. And then the other half is going to be mechanisms or ways, let's say, ways of, let me change my words a little, ways of transferring energy either into or out of a system. So, places to store energy. We've already talked about storing energy within a gravity field. Okay. So when you move an object within a gravity field, you can have UG. Now, you can also move, instead of moving a mass within a gravity field, you can move something else called a charge within an electric field. Now, we're not doing that in this unit, but that would be U electric, maybe. You move something within you move a charge within an electric field. But again, I draw a dotted line because we're not going to do that now. Or maybe you could move something within a magnetic field, in which case you'd have U magnetic. Okay? We're going to just worry about moving something within a gravity field. Okay? So I'll call this gravitational potential energy. And potential energy means it's energy that's stored based on an object's location. Okay? So object's location within a field. Okay? So that would be UG. Or you can also have U elastic. And this is like it's stored in elastic molecules. Okay? So energy stored by I'm trying to think of how to say it. By stretching or compressing elastic. By stretching or compressing elastic molecules. Okay? Like springs, rubber bands, bungee cords, things like that. So that would be an example of U elastic. And maybe you could also have U chem. That might be helpful for a few problems. There's some examples where having U chem might be helpful. Okay? See if I can write U chem. And then this would be stored in chemical bonds. Okay? Now, fossil fuels are a perfect example of that because you have these strong carbon bonds that you're breaking when you burn fossil fuels. Trying to think of what else we use. Now let's talk about those are all U because those are all examples of potential energy. Now I'll change to another color and we'll talk about K. And in this case we'll do K translational. And it's just kinetic means motion. And I'm gonna try a dotted line because later in the class, next semester, we'll talk about K rotational, which is different. Translational kinetic energy is the object's moving and you're not worried about any rotation. You just pretend, you take the center of mass of the object and you pretend that's the object. It's really making the object a point particle. Just like we've been doing with our force diagrams, you would represent the object as a dot or something. And the kinetic energy is the motion of that object as a whole, how it's translating through space. And you're ignoring any rotational energy, because rotational motion is also something moving. It's also energy. So we're not going to account for that this semester. We're just going to ignore it. So the primary places we can store energy right now this semester are going to be K translational. We'll have an equation for that. U chem, we're not going to have an equation for, but it's a cool idea. U elastic, we'll have an equation for. So when you stretch or compress a spring, and a rubber band, a bungee cord, anything of that nature. And then gravitational potential energy, we're going to discuss that as well. And we'll have equations for UG, U elastic, and K translational. All right, and primary ways of transferring energy into or out of a system. Well, there's just going to be two, and the main one to make energy go in or out is just when a force is exerted on a system. So when a net external force acts on a system, and this force, I'm not going to worry about the equations now, but let's just say when there's a force acting, the simplest case would be same direction as object moves, then we'd be talking about energy going into the system, energy transferring into system. On the other hand, so that's like if you take a box and push it and it speeds up, you've transferred energy into that system. Okay? Now, on the other hand, if your force acting on a system is opposite the direction, this is actually system, not object. The direction the system moves. So if there's an external force, a net external force, acting opposite the direction the system moves, then energy would be transferring out. Out of system. Okay? Now, we call this, we call it work in physics, work done on a system. It could be taking energy out, it could be putting energy in. It's always called work done on a system. And I like to add an ing. In textbooks, you'll just see the word work, but since it's energy that's transferring, I put an ing at the end to remind myself that it's energy that's transferring over a time interval. Okay? It doesn't happen at a moment in time. So this happens over a time interval. And when you look at energy stored, on the other hand, you're looking at a moment in time, the beginning and the end. So there's a difference in the way we use these terms. And then we also have like a catch-all phrase. I'll just make a new slide for it. It's pretty important. So catch-all phrase for energy stored, sorry, not energy stored. This is energy transferring. And I like to define my system so that energy transfers out. Air resistance, it's like a catch-all phrase. Air resistance, friction, sometimes we say friction does work on an object, or we can say that we can account for it this way as well. I'm trying to think of other examples. Any kind of fluid resistance. We have a catch-all phrase for this, and we say energy dissipating. Again, I use the ing for energy dissipating out of a system over a time interval. So this is in the middle of your energy flow diagram. And the symbol we use is EDIS. Stands for energy dissipating. Anyway, I hope that helps. And those are the basic places we can store energy and the ways in which we can transfer energy into or out of a system.